In this lecture, I want to talk about the product rule, which is how do we take the derivative of something that is the product of two or more functions. All right, so we're looking at this, it's x times e dx. The first thing I want to do is explain how we don't take the derivative of this. Here's the temptation. We want to say that f prime is the derivative of x, which is 1, times the derivative of e to the x, which is e to the x. That is not how it works. All right. One way to see why that fails. Let's say if we had that f of x was equal to x squared. All right. Well, we know that f prime, using the power rule, we know that that's 2x, right? But if we use this idea where we just took the derivative of each of them, I could rewrite this as x times x, right? And if we use this idea that the derivative of the product is the product of the derivatives, well, the derivative of x, then we would get that f prime, the derivative of x is 1 times the derivative of x is 1, which would just be 1. But we already know, clearly, this is the derivative of f, not this. So this kind of nonsense doesn't work. It would be nice if it worked out that way. I'll be the first to admit that, but that is not how it works. So and I want to rewrite this. The reason I'm using this big F is I want to reserve little f and little g is kind of the functions that we're multiplying in this product. So in order to get a product rule, we need a product, and it's the product of two functions. So let's go back to our definition. So we're taking the derivative with respect to x of f of x times g of x. Well, our definition says that that should be the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. Well, that doesn't seem particularly helpful. I mean, we've got to start here. We would like to get a general rule, so that part of it's helpful. But this is going to take a little bit of, I would say, unintuitive or unmotivated algebraic manipulation in order to get this to work out for us. So what I'm going to do is I'm going to add to this f of x times g of x plus h, I guess I don't really want that there, minus f of x times g of x plus h, all right, all over h, all right. So this is basically adding 0, right? I have f of x times g of x plus h minus f of x times g of x plus h, and I put it over h because what I'd like to do is combine this into one single term. And what I'm actually going to do is rewrite this. So I have limit as h goes to 0. I'm going to keep this first part out front. All right, f of x plus h times g of x plus h. Now I'm going to bring this part, well, I'll go ahead and write it first and then we'll see where things came from. So minus f of x times g of x plus h plus f of x times g of x plus h minus f of x g of x all over h. So all I really did here is I took this piece and kind of inserted it in right here, right after this. So here it is here, and then I took this piece and I inserted it right after that, so we see it right here. Okay, again, because we have a common denominator of h, we can just kind of play around here with the numerator. So I inserted these in between, so we see that this is still first and this is still last. And you'll see why I did that, because ultimately what I'd like to do, this puts my g of x plus h's together, right? So what I can do now is do a little bit of factoring, pull out a g of x plus h. From these two terms, that leaves me with f of x plus h minus f of x. So I have f of x plus h minus f of x. And then over here, the common term is f of x. So if I pull out and f of x, I am left with g of x plus h minus g of x. And maybe you're beginning to see the motivation here. Notice this is f of x plus h minus f of x. Here's g of x plus h minus g of x. If I can get those over h and take limits, then that's going to look an awful lot like f prime, and that's going to look an awful lot like g prime. So that's kind of where this is headed in terms of why do we insert these things. We inserted them so we can kind of move things around and factor and get things to fall out for us. So remember that the limit of a sum is the sum of the limits, as long as those limits exist. Since g and f are differentiable, so I guess that's the first part I should have said, is that f and g are differentiable functions, and we're trying to find what the derivative of their product would be. So I'm going to rewrite this now as the limit as h goes to 0 of g of x plus h times f of x plus h minus f of x over h plus the limit as h goes to 0 of this piece, f of x times g of x plus h minus g of x over h. Okay, can I squeeze one more down here? I think I can. So now the limit of a product is the product of limits, as long as those limits exist. And since g and f are both differentiable, therefore also continuous, we know that these individual limits exist. So I'm going to write this limit as h goes to 0 of g of x plus h times the limit as h goes to 0 of f of x plus h minus f of x over h. There's no h underneath here, because if I had an h underneath here, then when I multiply it, I would get h squared. I'm going to include the h over here because obviously this is f prime by definition. Alright, now I'm going to do the same thing over here. So I'm going to rewrite this as the limit as h goes to 0 of f of x times the limit as h goes to 0 of g of x plus h minus g of x over h. Again, I want the h over here because this is g prime. So let's just look at what we have going on here. This is f prime. This is g prime. So it's important to know that we're starting off with differentiable functions, otherwise we wouldn't know that these limits existed. But there's f prime, there's g prime. Now, notice here, since g is continuous, I can just substitute 0 for h, and I'm just left with g of x. And here there is no h, right? There's no h in this, so that's just going to be f of x. So notice what I have here. So that's g of x times f prime plus f times g prime. So that gives me a nice clean, so if I rewrite this again real quick, so here's f of x, it's f of x, well, big F is little f times little g, where f and g are both differentiable. Then what I end up with is g times f prime plus g prime times f. Of course, this is equivalent to if I wanted to say, f prime times g, if you like your f before your g, plus f times g prime. I could also flip these, right? So there's a lot of leeway here because multiplication is commutative, so I can switch these, but addition is commutative too, so I could switch these. The point here, if you see kind of the big picture, is for the first half of this, I take the derivative of one of them and leave the other one alone, and then I add, and then I switch. So I took the derivative of f the first time. So for example, this also could be, if I took this piece and made it first, I would have f times g prime plus f prime times g. That's just switching these to take this, put it over here, take this, put it over here. It doesn't really matter. But again, the big picture, you take the derivative of one of them, leave the other one alone, plus the derivative of the one you haven't taken yet times the other one. All right? So what would that mean for the function that we started with, x e to the x? Well, I could take the derivative of x, that's 1, times e to the x plus, so that's the derivative of x times e to the x plus x times the derivative of e to the x, which is e to the x. You know, and a lot of times your book will simplify by factoring out an e to the x, right? So we end up with 1 plus x. Okay, so there is one example of how to apply the product rule. Let's see a few more. I don't know, we got some space left here. Let's take a look at something like h of x equal to x cubed plus 1 times 2x squared plus 8x minus 5. All right, so for h prime, let me just first kind of lay this out. I'm going to take the derivative of the first one times the second one plus the first one times the derivative of the second one. All right, so now we just have to actually do these derivatives, which really are just, in this case, a matter of using the power rule. So I would get, well, the derivative of this is 3x squared, and the derivative of 1 is 0, so that is the derivative here. So I have 3x squared times, and then I'm just going to rewrite that, right? For the first part, I just leave one of them alone and take the derivative of the other. Plus, then I'll end up with x cubed plus 1 times the derivative of this. All right, so again, using the power rule on each of these, this is going to just be 4x to the first power, but we just write x. 8x, the derivative of 8x is just 8, and the derivative of any constant is 0, so I'm just left with this. So there you have it. That's the product rule. Let's just do one more example here. And actually with this example I will use a new page. So let's look at something like f of t equals the square root of t times 1 minus t. All right. Well, again, we want to use the power rule whenever we can. So I'm going to rewrite the square root of t as t to the 1/2 times 1 minus t. Okay, so then the derivative, I'm going to take the derivative of the first one. So I guess I'll just write it. I'll give us kind of the plan first. We'll take the derivative of that times 1 minus t plus t to the 1/2 times the derivative of 1 minus t. Okay? Well, the derivative of t to the 1/2, that's 1/2 t to the negative 1/2, right? And then I just leave this as 1 minus t plus t to the 1/2. Now here, 1, derivative of 1 is 0 because it's a constant, and the derivative of minus t is negative 1. All right, because you can kind of think of that, well, like negative 1t, and so it's like a linear function, so we're just left with the coefficient right there. So we could clean this up a little bit if you wanted to. So we could rewrite this as 1/2 t to the negative 1/2, 1 minus t, and then that's just minus t to the 1/2. I mean, we could go further if we wanted to, but this is about taking the derivative, not about doing algebra. I just wanted to point out with this one, however, that just because I have a product doesn't necessarily mean that using the product rules is the best way to go. Because notice here, I could actually simplify this to begin with, right? So just to kind of, I'll put it in a different color, because this is another technique. I can distribute the t to the 1/2, right? So t to the 1/2 times 1 is t to the 1/2, and t to the 1/2 times t, 1/2, and t to the 1/2 times t, well, that's t to the first power. T, if the bases are the same, I add the exponents. 1/2 plus 1 is 3/2. All right. Now f prime of t is just a simple application of the power rule. Minus 3/2 t. When I subtract from here, that's going to leave me with